go. So we are going to continue with 7.5 today. 7.5 continued. This kind of all falls in the category of what we call logistic integration. Alright, so when you have an integral, you got to integrate. Let's talk about the different ways we do it. First thing we look to see is, one possibility is straight integration, right? Or you can say antiderivative, which way you guys want to say it? Straight integration? Alright, sure. Alright, if you can do straight integration, then we always look for an algebraic way out of it, right? I'm just going to say algebraic change. So it's the second thing we look for, right? If that doesn't work, then we look at that whole U substitution thing. Then, what we talked about yesterday is if you can't do any of those, and you have this beautiful, big, ugly fraction thing happening in your integral, we're going to do partial fractions, which is what we did yesterday. Okay? Now, a partial fraction happens when the denominator exponent is greater than the numerator exponent. The last thing you're going to look for is if that doesn't work because maybe the denominator is smaller than the numerator, you're going to divide. And I'm going to put long division because you guys love that stuff. And that's if, whoops, move up, if the denominator exponent is smaller than the numerator. Alright, so here we go. We're ready for the first example? Alright, example number 1. Here's our integral. We have 2x plus 16 divided by x squared plus x minus 6 dx. Alright, so if we actually look through the different things we talked about, 1, can we do straight integration? No. 2, algebraically, we could look to see if we factor and we can try and cancel stuff. That doesn't work here either. 3, a u substitution. Remember, a u substitution, when you do the derivative of that u, it has to match the rest of it. Does that happen? No. So that doesn't work. So now we're going to go to partial fractions. Because the denominator is bigger than the numerator, we do partial fractions. If it would be the other way around, we'd divide. And we, of course, will get to one of those. Okay? Alright, so partial fractions is what we did yesterday. Partial fractions is breaking the fraction into 2 separate pieces, undoing a common denominator. So the first step to that was factoring this denominator. I draw myself a little x over here, negative 6 on top, 1 on the bottom. My sides are 3 and negative 2. So that means this is factored into x plus 3 times x minus 2. Which means as partial fractions, we're going to break this up and say we have a over our first factor of x plus 3 plus, we're going to use the letter b over the second factor of x minus 2. We're going to break it up into 2 pieces. Alright? Now we're going to do that whole common denominator equation thing. So what I'm really doing is I'm taking this piece and multiplying it times a, this piece multiplying it times b, so we can put them back together, and setting it equal to the numerator. So I'm going to take a times x minus 2 plus b times x plus 3, and this has to equal, move that out of my way, 2x plus 16. Next thing we decided is what are our zeros of those factors? What's the zero of the first one? Perfect. And what's the other one? Good. So let's plug negative 3 in first. Okay? If I plug negative 3 in for x, I get a times negative 3 minus 2 plus b times negative 3 plus 3 equals 2 times negative 3 plus 16. So I get negative 5a. My b drops out because b times 0 is 0. Negative 6 plus 16 is 10. So my a value is negative 2. Alright, now we're going to plug in 2. So if I do it again, I plug in 2, I get a times 2 minus 2 plus b times 2 plus 3 equals 2 times 2 plus 16. Right? Okay. So here, 2 minus 2 makes my a drop out. So I get 5b equals 20. So b equals 4. Alright, so now we're going to go back and rewrite this. I'm going to move this up just a little bit. So in my integral, I actually have a, which is negative 2, over x plus 3, plus my b, which is 4, over x minus 2. Whoops. Come on. And then technically it's all dx at the end, right? So any question at that point? It doesn't, when you solve it, you have to put it over the one you solved for. Do you know what I mean? But it doesn't matter when you start. Like if I would put x minus 2 here and x plus 3 here, it just means that this one would have been 4 and that one would have been negative 2. They just would have switched places. Right. Because the whole idea is if I were to put this back together, I would multiply this one by x minus 2 and that one by x plus 3, and then it'd all go back together. So we've just broken it apart. Alright, so now we're going to integrate this. Technically, what's going to happen, and we're going to end up shortcutting it a little bit, but if we look at this first piece, if I were to do a u substitution for the denominator, x plus 3, my du would simply be dx, right? So in this first one, if I was to break this up into two separate integrals, if I were just do the first one, I would actually do the integral of negative 2 over u du, right? Which this would be negative 2, antiderivative 1 over u is the natural log of u, right? Okay. Then I would do the same thing here, and I can say it's a whole separate one, but it's going to be 4 over u, technically, a different, or v, dv. So this is going to be plus 4, the natural log of this denominator, and then plus c. So let's plug those back in. So our answer, we have negative 2, the natural log of u, in this case, is x plus 3, plus 4 times the natural log of the denominator of this one, which is x minus 2, plus c. Alright, so here's where the fun comes in. Back to our algebra. Alright, first of all, natural log rules. If I were to write these in the other direction, it'd be this one minus that one, right? Correct? And in the log world, when we're subtracting, we're really dividing. Okay? And then this number that's in front, what is it actually? The exponent. So we can actually put this 2, just the 2, not the negative, gets to go on this. This 4 gets to go on this one. And because this one's negative, this part's going to go on the bottom. So this is actually the natural log of x minus 2 to the 4th over x plus 3 to the 2nd plus c. If you left it in that form, that's fine. We're just condensing it down, doing our log rules, and putting it together. Any question on why it's those places? No? We're good? Let's do another one. Example number 2. Alright, let's go with the integral of 2x to the third over x squared minus 1 dx. Alright, can we do straight integration? Is there any way to do algebra to simplify this down? Can we do a u substitution? No. Is the exponent greater on the top or the bottom? This time it's on the top, right? So now we're going to have to do long division to break this apart. Okay? So, here we go. In long division, this is x squared plus 0x minus 1 divided by 2x. I just wrote that backward. Whoa, my bad. Sorry, guys. I just wrote that backward. My bad. Let's try that again. 2x to the third. Whew. Divided by x squared minus 1. That's better. What times x squared is going to give us 2x to the third? 2x. I agree. 2x times x squared is 2x to the third. 2x times negative 1 is negative 2x. Draw my line. Of course, change my signs. We talk about that all the time. And we get this 2x to the third. Oops, 2x to the third. Wow. 2x to the third minus 2x to the third. Those are going to cancel. And I have 2x. All right, do I have anything else to bring down? So what I actually have here is 2x plus 2x over x squared minus 1. Right? Remember how we took our remainder and wrote it over the front? Alright, so here's our integral we have. We actually have the integral 2x plus 2x over x squared minus 1. And technically it's all dx. So questions on dividing it at all before we keep going? Nope, okay. So this one, now remember one of the rules we did in the very beginning is we can actually make it into 2 separate integrals, right? We can integrate the first one and then we can integrate the second half. So we can say this is the integral of 2x plus the integral of 2x over x squared minus 1. Dx, of course, on both of them. So in this first one, can we do straight integration? Yes, we can. 2x means technically we have 2x squared over 2. And our 2's will cancel. Plus. Alright, how do we want to integrate this one? This time we can do a what? A u substitution. U will equal x squared minus 1, which means our du is going to be 2x dx. So we actually have the integral of 1 over u du. So antiderivative 1 over u. Natural log u. Then we have plus c. So what do we really have? We have x squared plus the natural log. And I'm going to put it in my absolute values because it's just the u. X squared minus 1 plus c. Not bad at all. Okay. Let's try one more, and I think I want you guys to try some. All right. Let's do one more with the partial fractions. Okay. All right. So let's look at this. Example number 3. I mean, the best way for us to get through this is for us to try them and trial and error, see what it is we're still like questioning. So let's say we have go with 5x plus 14, the integral, over x squared plus 7x dx. Whoop. Alright, so we can see that there's nothing algebraically we can do with that, right? You can see that if I did a u substitution for the bottom, the derivative would be 2x plus 7. That doesn't help us at all. Okay. So then we're going to break this apart because the denominator is higher than the numerator. So we're going to actually factor this. What can I factor in x squared plus 7x? Take out an x. So I have x times x plus 7, right? So I'm going to rewrite this as a over x plus b over x plus 7. Alright, so then I'm going to have a times x plus 7 plus b times x equals the 5x plus 14. What are our zeros we have here? X equals what and what? Good. 0 and negative 7. Let's start by plugging in our 0. So I plug 0 in. I put 0 in for x, I get 7a. The b drops out, right? Equals 0 plus 14, or 14. So a equals 2, right? Okay. I kind of like talked through this. So I put 0 in here, that drops out. 0 in here, there's none of that. Now if I put negative 7 in, this time my a is going to drop out. I get negative 7b equals 5 times negative 7 is negative 35 plus 14, negative 21, yes. There we go. Divide both sides by negative 7 and we get b to equal 3. Alright, so let's rewrite our integral. We're going to have the integral of 2 over x plus 3 over x plus 7, all technically into dx. So tell me what's the antiderivative of 2 over x? Good, 2 natural log x, I agree. Plus, what's the antiderivative of 3 over x plus 7? 3 natural log x plus 7 plus c. Alright, so how can we put this together this time? Remember that these are exponents, right? And they are adding, so they're multiplying. So this is the natural log of x squared times x plus 7 to the third plus c. Yeah? Alright. So today I want you to do 5 through 21 odd, but omit number 9. Simply because it's a tangent inverse, and we love those inverse ones. Okay? Yes, please. Just add it on to yesterday's. It's perfect. Or if you haven't done yesterday's yet, you can add yesterday's onto the end, or however you want to do it. Whatever works for you.